StatQuest, naive babes, gonna talk about it, clearly explained. StatQuest. Hello, and welcome to the StatQuest live stream. I'm glad you guys are all here. I'm really excited about today's StatQuest, and I hope you guys are excited about it too. We're going to be talking about naive Bayes, and it's going to be clearly explained. I see in the chat we got lots of hellos. Hello, everybody. We got someone from Luxembourg, some people from India, people from Brazil, people all over the world. This is very exciting. Just checking. Someone said no audio. Is that correct? Are you guys getting any audio? Maybe someone post a comment. Maybe I will. I'm going to write in a comment real quick. Are you getting audio? Got someone from Texas, Tunisia, greetings from Germany, Toronto, Poland, holy smokes, Greece. Yes, you have audio. It's been confirmed. You can hear what I'm saying. Thank you very much. Let's talk about naive Bayes. China, holy smokes, Russia. Oh my gosh, this is very exciting. And India, Netherlands, wow. This is just blowing my mind. It's not common to talk to everyone in the whole world. At least have most major countries represented. Turkey, holy smokes. More India. All right, this is very exciting. Okay, enough of me just getting all excited about the chat going on right now. Let's talk about naive Bayes. I'm going to be focused on that. All right. So I have a theory that the simpler the machine learning method, the more jargon is used to make it seem complicated. Naive Bayes is a good example of this theory in action. It is chock-a-block full of fancy jargon, and it's really one of the just most straightforward, simplest machine learning methods out there. So we're just going to skip the jargon for now and dive right into an example that shows how it works. Imagine we received normal messages from friends and family. And we also received spam, unwanted messages that are usually scams or unsolicited advertisements. And we wanted to filter out the spam messages. So the first thing we do is make a histogram of all the words that occur in the normal messages from friends and family. We can use the histogram to calculate the probabilities of seeing each word, given that it was in a normal message. For example, the probability of we see the word deer, given that we saw it in a normal message, is 8, the total number of times deer occurred in normal messages, divided by 17, the total number of words in all of the normal messages. And that gives us 0.47. So let's put that over the word deer over on the left side so we don't forget it. Likewise, the probability that we see the word friend, given that we saw it in a normal message, is 5, the total number of times friend occurred in normal messages, divided by 17, the total number of words in all of the normal messages, and that gives us 0.29. So let's put that over the word friend so we don't forget it. And likewise, the probability that we see the word lunch, given that it is in a normal message, is 0.18, and the probability we see the word money, given that it is in a normal message, is 0.06. Now we make a histogram of all the words that occur in the spam. and we calculate the probability of seeing the word deer, given that we saw it in the spam. And that is 2, the number of times we saw deer in the spam, divided by 7, the total number of words in the spam. And that gives us 0.29. Likewise, we calculated the probability of seeing the remaining words given they were in the spam. I'm going to go back one slide. Look at that. The word lunch is not seen in any of the spam, so the probability of seeing it is 0. That's going to come to haunt us later on, but then we're going to come up with a workaround to fix that problem. But so I'm kind of giving you a sneak peek of what's going to happen later on, but for now we're just going to let that be 0. It's not going to bother us for this first example. Okay, bam! Now, because these histograms are taking up a lot of space, let's get rid of them but keep the probabilities. So we just got the probabilities on the left side of the screen instead of the histograms. Okay, now imagine we got a new message that said, "Dear friend." It's a very short message, but it's an example. Okay, if we want it to decide if it's a normal and we want to decide if it's a normal message or spam. We start with an initial guess about the probability that any message, regardless of what it says, is a normal message. The guess can be any probability that we want, but a common guess is estimated from the training data. For example, since 8 of the 12 messages are normal messages, our initial guess will be 0.67. So let's put that under the normal messages so we don't forget it. Now we multiply that initial guess by the probability the word deer occurs in a normal message, and the probability that the word friend occurs in a normal message. Now we just plug in the values we worked out earlier and do the math. And we get 0.09. In a simple way, and probably actually more than just simple, probably in a proper way, we can think of 0.09 as the score that dear friend gets if it is a normal message. However, technically, it is proportional to the probability that the message is normal, given that it says, "Dear friend." So let's put that on top of the normal messages so we don't forget. Now, just like we did before, we start with an initial guess about the probability that any message, regardless of what it says, is spam. And just like before, we can guess. The guess can be any probability we want, but a common guess is estimated from the training data. And since 4 of the 12 messages are spam, our initial guess will be 0.33. So let's put that under the spam so we don't forget it. Now we multiply that initial guess by the probability that the word deer occurs in spam, and the probability that the word friend occurs in spam. Now we just plug in the values that we worked out earlier and do the math. And we get 0.01. Like before, we can think of 0.01 as the score that dear friend gets if it is spam. However, technically, it is proportional to the probability that the message is spam, given that it says "Dear friend." And because the score we got for normal message, 0.09, is greater than the score we got for spam, 0.01, we will decide that "Dear friend" is a normal message. Double bam! Now, before we move on to a slightly more complex situation, Let's review what we've done so far. We started with histograms of all the words in the normal messages and all the words in the spam. Then we calculated the probabilities of seeing each word given that we saw the word in either a normal message or spam. By the way, this is a terminology alert. It's not really part of the StatQuest because I don't think it's super necessary to know this because it's pretty intuitive. But technically, these probabilities are called conditional probabilities. And up on top, we have the conditional probability of seeing deer given that it's in a normal message. That's sort of the statistical lingo for how you would say that. You'd say the conditional probability of seeing deer given that that's in a normal message is 0.47. So if you want to sound fancy, use the fancy terminology. Anyways, so we put those conditional probabilities over to the left. Then we made an initial guess about the probability of seeing a normal message. This guess can be anything, but we based ours on the classifications in the training data set. Then we made the same sort of guess about the probability of seeing spam. Then we multiplied our initial guess that the message was normal by the probabilities of seeing the words dear and friend given that the message was normal. Then we multiplied our initial guess that the message was spam by the probabilities of seeing the words dear and friend given that the message was spam. Then we did the math and decided that dear friend was a normal message because 0.09, which is what we got for the normal message, is greater than 0.01, which is what we got for spam. So there we go. We've classified dear friend as a normal message. Now that we understand the basics of how naive Bayes classification works, let's look at a slightly more complicated example. And by slightly, I mean this much more complicated. Naive Bayes is really, really simple, even when it gets complicated. Okay, this time, let's try to classify this message. Lunch, money, 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 money. Note, this message contains the word money 4 times. And since the probability of seeing the word money is much higher in spam, 0.56, than in normal messages, 0.06, then it seems reasonable to predict that this message will end up being spam. So let's do the math. Calculating the score for a normal message works just like before. We start with the guess. Then we multiply it by the probability we see lunch, given that it is in a normal message. And the probability we see money 4 times, given that it is in a normal message. And you'll notice, I'm not really pointing this out in the StatQuest explicitly, but you'll see that the probability that we see money, given that it's a normal message, is raised to the 4th power. So that's how we're going to kind of like keep this equation from going right off the edge of the screen. So we'll just use that exponent. Okay, when we do the math, we get this tiny number, a bunch of zeros, and then finally we get the number 2. It's small, no big deal. However, when we do the same calculation for spam, we get 0. And this is because the probability we see lunch in spam is 0 since it was not in the training data. In other words, any message with the word lunch in it will get 0 for spam. And that means we will always classify it as normal, no matter how many times we see the word money. And that's a problem. To work around this problem, people usually add one count, represented by a black box, to each item in the histograms. I don't want to get ahead of myself. When I start adding like random stuff that I'm just thinking about off the top of my head, I almost always say what's coming next. Okay, so note the number of counts we add to each word is typically referred to with the Greek letter alpha. If you're going to do naive Bayes and scikit-learn with Python, that's the parameter you're going to set. You're going to set alpha equal to something. I think the default value is 1 already, so you don't have to worry about it. But you can check that at your leisure. Anyways, in this case, alpha equals 1, but we could have set it to anything. Another term for alpha, by the way, and this is like, oh no, terminology alert. Another term for alpha is pseudo count. That's sort of the term I was kind of brought up on. Whenever you add extra numbers, it's called a pseudo count. But like I said, naive Bayes is chock-a-block full of terminology to make it sound fancier than it really is. We really haven't done anything that fancy by adding 1 count to every single word. Anyway, now when we calculate the probabilities of observing each word, we never get 0. For example, the probability of seeing lunch, given that it is in spam, is 1, that pseudo count, that extra count that we just added, divided by 7, the total number of words in spam, plus 4, the extra counts that we added to each word. And that gives us 0.09. So now, when we calculate the scores for this message, we still get a small number of normal messages. We still get a small number for the normal message. A little bigger than before, I think. But now when we calculate the value for spam, we get a value greater than 0. And since the value for spam is greater than the one for a normal message, we classify the message as spam. Spam! I've been waiting this whole StatQuest to say that. Okay, we're going to talk about why we do this math this way some other day, and what it has to do with Bayes and some other days. However, I will actually. We might talk about it now. I think we've got time. Let me just check my. Let me put this guitar down. Check the time. We have time, so we will in fact address that question of like what's going on technically. I don't have great slides for this. But we will talk about it in just a little bit. However, before we do that, I want to mention that I've got these sources. I'm going to put these links in the description of the video below as soon as we've saved everything. I should have already done it, but I'm running a little bit behind this morning, so I'm going to put those there. You don't have to copy these down. Anyways, I've got the scikit-learn information, including what the alpha value is, so you guys can look that up. And we're gonna say double spam. And now we're gonna do some viewer questions. And I saw over in the chat window that someone said I did not get that directly proportional part, where you said the probability of giving a word as spam is directly proportional to the probability. Yeah, so what's going on? Let's go back. Let's go back to where... Let's go back to here. Okay, this is where we're actually talking about the proportionality. You remember, this is we start on the left side with the probability it's spam times the probability we see a word, given that it's in spam, times the probability we see another word, given that it's in spam. So we see the word deer in spam and the probability we see friend in spam. And once we plugged in the numbers, I said this is proportional to the probability that the message is spam, given that it says dear friend. And this is sort of the magic of Bayes' theorem, which is sort of how this transformation works. The reason why it's proportional is Bayes' theorem, I mean, uh, divides typically divides the left side by a scaling factor to make sure that that value is going to be between 0 and 1 and it is actually a probability. And in this case, the way we're calculating the probabilities and everything, we're kind of guaranteed to get a value between 0 and 1, but there's still a scaling factor that Bayes' theorem sort of requires you to get an exact probability. And that scaling factor actually plays a much, much, much bigger role when you're using, instead of counts, like we used counts. We used the number of times we saw the word dear in spam and the number of times we saw the word friend in spam. So we were just counting these things. But if you're using a Gaussian distribution or a normal distribution to kind of model things like somebody's height, say like we're trying to predict gender based on their height and some other things, or not gender, sex, I guess that's the proper word for it now, based on their height and some other things, and we're using a normal distribution for those, that scaling factor plays a much bigger role because we're actually just using likelihoods in the numerator. And so in this case, we're using probabilities because we're using counts. So when we have discrete things that we're counting, we use probabilities because they're the exact same thing as likelihoods. But when we use a normal distribution or something like that to measure what we're using to make predictions, we're using likelihoods, and likelihoods can be much larger than 1. And that normalization factor, the thing that we would divide this equation by, we would divide this equation, the probability of seeing something that's spam, times the probability of dear, given that it's in spam, times the probability of friend, given that it's in spam. We would divide that by something to make sure that we're getting a probability, and scales it. So I don't know if that's the best answer to that question, but sort of given the slides that I have, it's sort of the best I can do. So yeah, the proportional thing is something that goes from Bayes' equation. However, it's all still a stretch because the naive aspect of Bayes is that the probability that we see dear in a spam message is considered to be independent of the probability we would see the word friend in a spam message. And so that's one of the things that makes naive Bayes very naive, because oftentimes words or things are correlated. And when they're correlated, you can't just multiply the probabilities together directly and get an accurate estimate of the true probability. So naive Bayes just gets rid of that complexity of dealing with correlations and simplifies everything by saying, hey, we're just going to assume there's no correlation whatsoever, and that's going to make me naive, but it's going to make me simple, and get this, surprisingly accurate anyways. That's sort of the weird thing about machine learning is we kind of throw away the how good the model is in order to, in a technical way, in a theoretical way, by making sort of like ridiculous assumptions, and when we throw those things away, we actually get a model that works great with actual data. And the reason why that has to do a little bit with the bias variance trade-off that affects all of machine learning by making this assumption that these words are not correlated or that everything's uncorrelated. We add a little bias to our model, so we're not like super accurately predicting the reality of the situation. But in exchange for that little bit of bias, we get a big reduction in variance, meaning we're doing a much better job predicting in our testing data set. Uh, so that's what that is. Uh, what else can we talk about with naive Bayes? Naive Bayes, um, I'll be honest, I'm just going to put this out there. I actually don't have a lot of practical experience. So what I'm doing is I'm just telling you what I read. Naive Bayes, let's talk about the advantages of naive Bayes. I haven't experienced these firsthand, but this is what people say about naive Bayes. They say it's great when you don't have much data, and it's also great when you have tons and tons of data because it's relatively easy to scale up to crazy large because it's such a simple model and it just relies on histograms. And if you saw the last XGBoost video, XGBoost Part 4, Crazy Optimizations, you learned about sketch algorithms barely. And we talked about the quantile sketch. And the quantile sketch is related to something called a histogram sketch, which is an algorithm that can rapidly approximate a histogram without having to look at any single value more than once. And that's kind of a big deal because usually when we do a histogram, we sort all of the observations and we have to count them, and that can kind of be a mess. Actually, what am I saying? A histogram is just counts. We don't even need a sketch algorithm. This is what I get for trying to think and talk at the same time. Um, we can do this histogram super fast. The data is coming in. We don't ever have to look at it more than once. The data is coming at us. We just look at a word and go, have we seen this before? Yes. We'll just add a count to that. No, we'll just say we've seen it once. And then we just keep going. And at the end, we've got our histogram. Bam. No big deal. Anyways, naive Bayes scales really well to really large data sets. And I've been told that it does a great job for spam and sort of like document classification. But again, I don't have a lot of experience with it myself. So, I want to give a shout out to Krishna Kavuru, who just joined as a member. Joining as a member is awesome. Joining my Patreon is awesome as well. Those are great. You get early access. I'm actually doing 2 p-value videos today. Like as soon as this live stream is over, I'm diving into recording and I'm going to post later today 2 videos on p-values. And all the members of the channel or Patreon members, they're all going to get early access to that. So they're going to get those videos today. So that's pretty exciting. Um, um, let's see what else we got over here. Someone wants to know about deciding to use naive method from several other learning algorithms. How do you decide that naive Bayes is a good method? When you've got a small amount of data, just try a bunch. And when you've got a lot of data, then your choices are limited, and that makes your life a lot easier. Um, it also kind of depends on sort of what you're modeling. Uh, Naive Bayes, typically from the examples I've seen, are counts or basic distributions. I haven't seen it used for image recognition, for example, or sort of like dealing with I guess, complicated data input. It's usually just counts or pretty straightforward um, distributions of, say, like height or something like that. You guys, there's some crazy stuff going on in the chats. Um, Someone asked about how correlation affects probability. Um, uh, and so, say like we've got 2 things, like the probability of seeing the word deer and the probability of seeing the word friend. Um, Obviously, I don't know. Maybe those 2 words are correlated. Maybe we often see dear friend frequently. Um, and so So if we frequently see them together, then if I see the word deer, then there's a good chance that friend's gonna be there. It's not just sort of an independent occurrence, and that lack of independence means there's correlation, like I said before. Um, but it means that just multiplying together, when we multiply two things together, we can only do that when they're independent. I guess I could do a quick stat quest on that next live stream. This is one of those things where you kind of have to see the math, and if I can't think and talk at the same time, I can't think and like write math out at the same time. That would be a total train wreck. But maybe that's something we can talk about in the next live stream. I can do a little preparation because that's the way I like to do it. I like to prepare. Um, uh, anyways, we've hit our 30-minute live stream. I know I started a little bit late, so I'm gonna let it run a little bit late. Um, but I think we're gonna call it an end of today's live stream. And I thank you guys for coming. I wanted to say, check it out. I'm wearing the StatQuest shirt. I want to thank everyone who's been supporting me, everyone who's getting T-shirts, everyone who's becoming members, everyone who's doing super chat or donating. That means a lot to me now that I'm doing this full time. Um, um, it means a lot to me, and it just reminds me that I do have one little war story that I want to give you guys. So a lot of you guys might know that a little bit over a month ago, I started doing StatQuest full time, and that was very exciting but very scary because I used to have a full time job, and I had a steady income, and I was able to pay all my bills and save a little bit of money for a rainy day and all that kind of stuff you're supposed to do. Um, but then I started doing StatQuest full time, and my revenue kind of went down, and that was expected, but it was also kind of a little bit of a panic, and I got a lot of offers to do some consulting work, and I thought, oh, if I do some consulting work, um, I can make up for the income thing, and I'll be doing StatQuest, but I'll be making enough money, and I'll be saving enough and paying all my bills, and it'd be great. Um, what I did, and this was a huge mistake, and I'm learning from this. So I took on so much consulting that I didn't have any time to do StatQuest, and I was like, wait a minute, I quit my job so that I could do StatQuest all the time, and now that I've quit my job, all I'm doing is consulting. Um, so what I've been trying to do is like streamline things and kind of thin out that consulting and do just enough that I can pay all my bills, but then still spend most of my time doing StatQuest. That is the goal, and I'm shifting back. I'm shifting back from that crazy consulting back to StatQuest, and I'm and I'm so much happier because yeah, the whole reason of doing this the way I'm doing it is so I can spend more time doing StatQuest, more time working on these live streams, getting them going. Um, so that's just sort of like a state of Josh Starmer and StatQuest update. And that's how we're going to end this one today. Thank you, thank you, thank you very much for joining me today. And we're going to give that a bonus bam and say the end. Thank you so much. All right. Until next time, quest on.